Okay, well, today we wanted to talk about in-ear monitor systems, and let's start in the right place. So why is he starting there? Well, other than watching the, the documentary that's recently been on TV. This is an interesting photo. This is the Beatles at Shea Stadium, 1969, the biggest rock concert ever. And if you look on that stage, you'll find, in addition to only miking the drum set with Ringo's vocal mic overhead, you'll see there's no stage monitors. These guys are standing in front of 30, 40,000 people, and nobody thought that we should give them a monitor system. So you can imagine what it must have been like to perform on stage without monitor systems. Anyway, just wanted to start there for background. So this is kind of what most people have that don't have in-ear monitors. You've got a bunch of wedges or, QSC K12s turned sideways, Mackie, whatever you got. We got these on stage. Interesting. We have four monitors and two house speakers. We got more for the band than we've got for the house, which arguably is a good thing, because if the band can't hear, then the performance won't be good. But anyway, with wedges, you're taking up real estate on the stage. You got to pack a bunch of stuff up in your truck if you're portable. You've got to drag cable, power, and speaker cables all over the place. It's big, it's expensive. The good side is it is dropout free for all those that are maybe worrying about going to wireless monitors. But that's about the only advantage I see on my side from in-ear monitors, where you can get a small pack like this. You can have a pack for your whole band, and you can put it in a lunch box. It weighs nothing. The cost is about equivalent to what a decent self-powered biamped 12-inch speaker would be, roughly. But the big advantage is that you have no feedback if you do this right, and also because the stage isn't full of your monitor mix, it's much easier for the sound guy to get a good mix, which is especially important if you're streaming, and lots of us are streaming these days. So you're going to end up with a much better performance actually going out over the air. And also you can do some things with in-ear monitors that you don't really want to do with wedges. For example, you could have a click track, for your drummer, if you've got backing tracks or something. That's easy to do in in-ears. And because most of these in-ears you can set up in stereo, for example, as opposed to just a stereo mix, you could have the click track in one ear and the monitor mix in the other ear, if that's what's comfortable for you. And also, with drummers, they don't necessarily, people that are in place don't necessarily have to have wireless in-ears. There are also wired in-ears, and you can make a mix of both systems, whatever works out best for your stage. But with wireless, so, the fear, I think, for a lot of people is, but we got to keep these on the air. They're unreliable. And I can tell you for a fact that a lot of people that I see are kind of starting out with this. It is unreliable because they're not thinking about this in terms of keeping their wireless radios, which is what these are. These are just wireless microphones. They're not thinking about keeping these on the air. And to keep these on the air, what you have to do, same way with your wireless mics, is the signal from your transmitter has to get to your receiver and get there and be at least 20 dB stronger than whatever the residual noise floor is at your venue, right? So everybody's got a noise floor. It's built out of a lot of things. If we look at this graphic representation, the noise floor on the bottom, the blue, that's caused by every other radio on the planet that's transmitting. That's caused by cosmic rays from outer space. That's caused by computer chips and motors and other things that generate RF interference. And these days we have some new interferers that we didn't have even a few years ago. LED lighting, whether it be your stage lights, whether it be lights in the house, definitely if you've got video walls, that kind of thing, video projectors, those all generate a little bit of junk, which adds to that noise floor and makes it higher. And a new phenomenon that's rapidly rising around the country is 5G cell phone service from T-Mobile, those pink lightning bolts. So as more and more people in your audience have 5G phones, and especially if they're using those 5G phones, so if they're streaming video back to somebody else in the world, they're creating more noise. And then of course you've got television stations, right? So depending on where you are, you could have a lot, a little, hopefully you've got gaps in between your channels. So anyway, in this representation, a long way to get around it, the top orange bar represents 20 dB above the noise floor at that particular frequency, right? So in this case, I've got wireless mics, but ears are the same. You can see the ones that are nicely above that noise floor. Those are going to be very reliable. I wouldn't worry about those. You can see there's a couple that don't rise above the orange bar level at the top. And while those still probably work, and maybe even work reasonably well, they're going to be chancy. I don't want those. They're probably you're going to have dropouts, or you're going to get swishing noise or something like that. That's going to happen with these. So we have to treat these just the same way we treat our wireless mics. It's pretty straightforward once you think about it. But you know, we have a limited amount of power. So really what we want to do is to shrink the noise floor. We have two tools to us usually when we're talking about wireless mics. We can either try to get the noise floor lower by using best practices, or we can shift to another channel. But shifting to another channel is becoming more and more and more difficult because we have less and less bandwidth than we used to have. If you're in a big city these days, you have, you know, well less than 10%, maybe only 6% of the available space to transmit in that we had 5 or 10 years ago. So your chances of moving to someplace that's clean is harder and harder. So what do we want to do? We want to shrink the noise floor. Well, the easiest way to do that is to get rid of a whole bunch of antennas, right? So we only want to have 2 antennas for our wireless mics and 1 antenna, although we'll talk about that, for our in-ear monitors. And because antennas interfere with each other, right? So as radio waves are penetrating those antennas, they create a current. Or in the case of your IEM transmitters, you're putting a current, which is creating a radio wave. And when these things are close together, they simply spill into the next antenna. And pretty straightforward. When you put antennas together like this, it changes the pattern of how they transmit. And it's when you have a antenna form like this, it's kind of hard to figure out where that pattern might be. So if you do something like this, typically what you're going to get is hot spots and cold spots. And we don't want cold spots, because if you're walking around and you step into one, your in-ear monitor is going to swish or go off the air. The other thing with in-ear monitor systems, pardon me, in-ear monitors, is that almost all of them are not diversity radios. In other words, the receiver has only a single antenna to pick this up. So with wireless mics, for example, we have 2 antennas, we have 2 receivers. And so hopefully you switch over to another receiver if your first receiver, if you step in a bad spot, hopefully at the same time your second receiver isn't in a bad spot as well. But with in-ear monitors, we don't have that chance, with the exception of some very expensive systems. So we kind of got to get this right if we plan to stay on the air. So how do we get, well, here, let's talk about this too. This is absolutely the worst thing you could do. In this rack, they've got their wireless mics and their in-ear monitors right next to each other. So you've got the in-ear monitors are transmitting, they're pitching, and the wireless mic antennas, they're catching. And when they're this close together, you can think about this in the same way you think about microphones and feedback, right? You can't point your microphone at the speaker, right? You got the speaker transmitting and the microphone receiving. So we've got the same thing with these pairs of antennas. And when they're this close together, they're you've got a loop going here that's going to degrade everything and probably knock you off the air. So this is a bad way to do it. The other bad way to do it is, you know, if you've got 6 in-ear monitor transmitters, is setting them all up, and especially setting them all up close to each other. If you were to space them, you know, 6 feet apart, you would remove that problem. But setting 6 transmitters 6 feet apart, it's going to take an awfully big desk to put them on. So what you want to do is combine all your transmitters to a single antenna. And we do this because we want to get rid of intermodulation. I'm showing it here with microphone transmitters, but you can imagine the same thing's happening if you go back to the rack and you've got all your transmitters together, or you've got, you know, 3 or 4 or 6 or 8 transmitters all sitting together on your mixing desk. When you get these things close together, you can see the intermod goes up. And those are sidebands. Those are phantom radio stations that you're now taking out of play. In other words, you can't tune to, when you see these other ones go up, you can't tune to those. If you have tuned to those or close to those, when your transmitters get close together, there's a good chance that they're going to take you off the air. So you're filling up the band that's already too tiny with more garbage. We want to eliminate that, or minimize, that's a better way to say it. So the way we do that, here we go, more examples here. This is on the red on the left there. That's separate transmitters, and we use a combiner. So you can see the noise floor. Remember, we're trying to get 20 dB away from the noise floor. So you can see by dropping these into a combiner, we can cut that noise floor down quite a bit. In this case, over 10 dB, right? We're looking for 20 dB, though a 10 dB improvement is enormous, right? That's really what's going to keep us on the air. So to do that, we use a combiner. This is essentially a unity mixer. If we were thinking about microphones, we plug 4 mics in to this one, and we get one signal with the combined 4 mics out. That's what we do with combiners. This is our 4-channel combined 4 unit, and we now have a combined 8 unit. And this will allow you up to 8 transmitters plugged in, going to a single transmit antenna. So this is a pretty easy thing to do. There's no magic in hooking this up. You simply plug it in. There's no adjustments. So you simply take your transmitter, your individual transmitter outputs, and you plug them in any order to the inputs of the combiner. Here we are just with the BNC cables, and so you know, we're shoving each of those transmitters into the combiner. That's going to resolve that to a single output. And then also the combiner, we supply this with a power brick that's going to allow you to power up all your units. So you don't have to use wall warts. And then you just take the single output and plug it into your transmit antenna. And there you go. In this case, we've got 8. You don't have to fill this up. You don't have to worry about it much. There's no adjustments. You simply just plug this in. So it's very easy to set up. When you do, the only adjustment you want to make is you'd like to turn the power down on your transmitters. And over here on the side, you can see, this happens to be with combined 4s, but you can see the difference that the transmitter power makes. Look at the noise floor at the bottom, right? So outside the transmitter, we can see that a low power level at the top, the noise floor is very low. And as we increase the power, the noise floor comes up, Remember, we got to go back to the basic. We're looking for 20. So if we add 3 or 4 or 6 extra dB to the noise floor, because we have our transmitters on high power, we're not getting as good a result as we could. So, so what you want to do, this is a page off the Sennheiser sheet, but it's this way for most units. Somewhere in the settings, you're going to see RF power level, and it's going to allow you to turn it up or turn it down. As far as I know, everything comes out of the box on high power. And if you think about it, with the little quarter wave whip antenna that they supply to you, that probably makes some sense, because that antenna is not very powerful and has a bunch of other things that could be a whole lot better. Anyway, it's just simple. You're going to go into the home screen somewhere. It's going to allow you to turn that down. We recommend turning it to the lowest power it will go. Unless you're trying to get somebody on an in-ear monitor on the other side of a football field. If you're on a stage, you're on a 50, 60-foot stage, you're 100 feet away, low power is going to work really nicely. And here's why. So EIRP, that's the effective power, not the watts, but the effective watts that come out of, or in our case, milliwatts. So if you turn your transmitter, your 50 milliwatt or your 100 milliwatt transmitter, if you can turn it down to 10 milliwatts, that would be turning your, if you had 100 milliwatts, that'd be turning it down 10 dB. But the antenna has 10 dB of passive gain, so you're right back to where you started. So if you put 10 milliwatts into this antenna, your effective power is going to be 100 milliwatts. So you're back to where you were, you're back to full power, but you've done it in a way that doesn't dirty up everything. So I know that's kind of funny. It's like, well, wait, I paid for this. Why am I turning it down? You're turning it down so it works better. So but all of these, regardless, even if we're using their little whip antennas that are supplied, they'll work better at lower power, right? So as long as we don't need the distance, which we rarely do because we're mostly going up onto a stage. So if we don't have guys running around a football field, the lowest power that you can use is going to result in the lowest amount of intermodulation, which means the lowest possible noise floor from all the electronics. So this is a real important thing. And not only that, you have to think about your in-ear monitor system. If you're using wireless mics, and I suspect most people are going to be, you have to think about all these together, because if you turn up your in-ear monitor system's power, you're also going to make it more difficult for your wireless mics to stay on the air and not be interfered with. So this is, like I said, they come out of the box on full power. You want to turn them down right away. Every decibel that you can turn down the power, you turn down the intermod by 3, right? So in this case of turning the transmitters from 100 milliwatts, if you happen to have 100 milliwatts, which by the way require licenses. So 50 milliwatts is what you're going to find on most in-ear monitor systems that are, $1,000 or less, and that's the maximum amount of power you can use. But if you were to turn your 100 milliwatts down by 10 dB down to 10, you turn the intermod down by 30 dB. It grows really fast, or it reduces very fast going the other way. So this is a major cause of dropouts to our wireless systems, both our in-ear monitors and our wireless mics. So using wireless mics, this is the strategy that you want to employ best you can for whatever you've got to make it easier to start with. Now, you don't absolutely have to do this, but it's, again, this is the best way to do it, and you should adopt something sort of close to this. So if we look at the top here, on the left-hand side, those are our wireless mics, and on the right-hand side, those are our in-ear monitors. And all the light blue underneath, that's all the intermod. So what we try to do is group these things close together, right? So if we look at the top if we look at the top graphic here, so our mics are all tuned within 5 megahertz, right? So if one mic was at 500, the highest mic in that group there would be at 505. Because basically what happens, the strongest intermod is the width of that cluster. So what we've done is we've added 5 megahertz. Wait a minute, gotta have coffee. 5 megahertz of primary interference, our third order interference, is going to be strongest 5 megahertz above and below that. In the same way, in this case, we've tuned all of our ears across 15 megahertz. So we're adding 15 megahertz above and below that band as our primary interference. And you can see we've got a nice big gap between the two. That's what we're shooting for. Because we don't want our ears to interfere with our mics, and we don't want our mics to interfere with our ears. Now, depending on the frequencies that you have available to you, because of the blocks, the tuning blocks of your units, and the channels that you have available to tune to, depending on your geolocation, you may have to expand those. So in the middle here, I'm showing if we had to expand the mics, in this case to 10 megahertz, and the ears in this case to 25 megahertz, you can see it spreads out, but we still have a gap in between. However, the bottom example, this is the worst case. If we have to expand that cluster even more, so in this case, if our mics are tuned from 500 to 520, and our ears are tuned from 550 to 600, just to make the numbers even, the intermods are going to overlap. And now your mics are going to interfere with your ears, and your ears are going to interfere with your mics. So what you want to do when you buy in-ear monitors is you want to get them in a group as far away from where your mics are as possible. Now, it doesn't matter which one's the high band and which one's the low band, right? If we could flip these around, the mics could be on top, the ears could be on the bottom. That's not going to make any difference in the real world. What we're looking for is that the mics are all the way at one end of the band as far as we can move it, and the ears are all the way at the other end of the band. And so when we do this, we end up with a nice gap in between, and we're preventing any extra interference, right? We've already got whatever our noise floor is there. We certainly don't want to add to it. So using this strategy is going to give you the best day. You're not going to have to worry about your system nearly as much. There's one other thing that we have to think about with in-ear monitors, and we think about this with wireless microphones and diversity systems, but since in-ear monitor systems almost exclusively only have a single antenna, we have to talk about this. This is more important than when you have diversity. So if you look at a normal antenna, this could be a whip or a paddle, they transmit. So if your antenna is, in this case, vertical, straight up and down from 12 o'clock to 6 o'clock, and your receiver on your belt is straight up and down from 12 o'clock to 6 o'clock, you'll get maximum transfer, and that's what you want. On the bottom half, we're showing with our CP beam antenna. This is what's called a circular polarized antenna. This is very important for in-ears because when you have only a single antenna, this type of antenna transmits the waves, spinning them around. So this is transmitting in 360 degrees at the speed of light. So you're not going to be in the wrong spot. So what happens with this, because it's moving, you're going to get anywhere between no loss and a little bit of loss, maybe 3 dB. But when we turn, so if our belt pack turns, you're bending or twisting, this is now at a 45-degree angle, you definitely lose a solid 3 dB off a stationary antenna, where with the CP beam antenna, you never lose more than that 3 dB. So your loss is somewhere between none and -3 compared to -3 consistently with a single polarized antenna. Now you're probably still good at this point. I wouldn't expect much of a problem from this. But if you manage to turn all the way horizontally, in this case, you would lose 21 dB. So, you're receiving, like 120th of the power that your transmitter is transmitting. Your antenna is just not able to soak it up because it's not pointed to it, right? Radio waves are directional. And so because the direction is spinning on the bottom with a circular polarized antenna, you'll never lose more than 3 dB. So it doesn't matter whether you're stage diving, rolling around, tumbling, moving. And the other part of this is some of these systems don't have stiff antennas. So if you have a system that has just a little piece of wire, a soft antenna, it may curl up on you. So that antenna is already partially, it's partially vertical and partially horizontal. So actually a neat little trick to those, if that's the kind you have, is get yourself a soda straw, stick the antenna in the straw to keep it real straight, and put a little tiny piece of tape on it. That's a little Broadway show trick. So anyway, it's very important that you use a circular polarized antenna, because otherwise, as you're moving around on stage, inevitably you're moving. That's why you want wireless. And you're going to be twisting. So your radio's, your belt pack's ability to pick up the signal is constantly changing as you're moving. Its signal strength is going up and down. And a lot of times, well, here I'm showing it going off the air, but that will produce swishing in a single analog radio. And almost all these in-ears are analog at this point. So you definitely want to use a circular polarized antenna. And with all things RF, you can mix brands all you want. There's nothing particularly exciting. We all use the same cosmic RF, right? Nobody has a proprietary RF. So brand A's antennas work with brand B's transmitters and brand C's receivers. And you can, excuse me, I didn't say that. You can't use Shure's transmitter with Sennheiser's receiver or some other brand, but you can use Shure brand and Sennheiser together. So, if you get a new guy joins your band and he's got some other brand, it's not a problem. You can just plug it in. It doesn't matter whether it's digital or analog, again, because all RF is analog, right? The energy, the radio wave is an electromagnetic wave. It's an analog wave. When they talk about digital wireless, what they're talking about is the coding scheme, the way they modulate the signal. So you can do that any number of ways, but it doesn't matter. They're all going to work together. So I hope that's kind of removed a lot of people's fears from getting into in-ear monitors. It's very easy to set up, but you have to use a combiner when you've got more than a couple of them. And you really, really, really need to use a circular polarized antenna to stay on the air. And if you do that, you should have a very reliable system. Once you get used to using in-ear monitors, you'll wonder how you ever did it any other way. Sometimes there's a slight learning curve. It's a little bit different, but usually after you put in a few hours with it, it's so much better. You can clearly hear everything. You won't muddy up your mix. Your monitor guy's gonna love you. If you're a traveling band, you may even want to take your own little mixer, especially if you get a little digital mixer where you can preset everything, and you just take splits off your board, and your monitor system will be exactly the same every place you play. You don't really even need to touch anything if things on your stage don't change very much, because it's in ear. So we're taking the acoustics out of the problem. So I hope that makes it a little more understandable, how to set up an in-ear system, and hope you try it, because you'll really like it, and you won't have to lug around a bunch of heavy stuff out of the back of your truck. So with that, we'll turn it over to any questions we didn't get answered. Mr. Adam, we got any there?
Thanks, Don. That was awesome as usual. We have three questions, so let me start at the top here. Any recommendations for multiple IEM receiver body packs on one transmitter?
Oh, well, you can basically use as many as you want, right? So, I mean, think about it this way. Channel 24 on TV is broadcasting to 60 million people with television sets on the other side. So there's a basically unlimited number you can use. So if you don't need a separate mix, right? So if all your vocalists are going to take the same mix and you got 6 vocalists, you can use one transmitter, but you can have 6 belt packs all picking that up. They'll all hear exactly the same thing. If that's okay, that's fine. Sometimes different people need to hear different mixes. Mostly, everybody wants the more me. So yeah, I want the vocal mix, but I want more of me in it so I can hear me. So you have to work those things out. But on the radio end of that, there's no problem. You can use dozens and dozens and hundreds. In fact, I can tell you where they did that. We worked with the guys that did the Tokyo Olympics. And if you saw the opening ceremony, they literally had more than 1,000. Every single person you see out there dancing has an in-ear monitor. And so they literally, all those guys on the field dancing and, doing all that stuff, they all had an in-ear monitor. And, they're all listening to the same mix because they got to hear the music and the timing cues. So they're all hearing the same mix. So there you go. One transmitter with over 1,000 receivers.
Wow, excellent, Don. All right, here we go. So Henry asks, how many meters of cable is going to need a booster? 50 feet, 100 feet, 200 feet?
Well, okay, with in-ears, first of all, you have to have a very special booster. So this is going to be, it's got to be way powerful because of the quality of boosters. It depends on your cable. There's lower loss cable and higher loss cable. And so again, you're going to get some loss for your cable. So the small cables like RG8X have about, it depends on frequency, roughly 8 dB of loss per 100 feet. Now, if that's too much loss, remember this, how much loss is all back to that 20 decibel thing, right? So when we have loss in the cable, that's coming down from the top. Where we have more noise, that's coming up from the bottom. And we don't care which end it came off of. We just need to keep 20 dB between those two. Obviously, we'd like to not lose it on either end. So the better answer for that, probably the lower priced answer for that, is to use a better cable. A bigger diameter cables have less loss. So if you were to use a coax like LMR 400 or Belden 9913, that essentially cuts that loss in half. So when you use that cable, so if you're using 100 feet of RG8X and you switch it to 9913, it's going to think now that you've got 50 feet of cable. So it's pretty easy to keep that, cables. Coax cable generally is a good solution up to about 200 feet. Beyond that, now you've got to get into some specialty stuff. But short of that, usually your best solution is just pick a better cable.
Awesome. Thanks, Don. The questions are raining on us, so I'll continue here. In regards to transmitting antenna for wireless microphones, will the benefits of a circular polarized antenna work on the receiving side?
Yes, although for belt packs, so for belt packs wearing on your waist, you're going to have to wear that antenna on your hat, I guess. It'll be one of those ones with the propellers that spin. So that's not going to be much of a solution. People do this a lot of times if they're doing remote point-to-point. So some people use in-ear monitor systems so they can set up a speaker 100, 200 feet away and transmit to it without having to run cable and all that. In that case, yes, you can use a circular polarized antenna in place of the other one. Most belt packs don't have a connector, so you have to look at that and see, that you have a receiver that can do that. You know, with the Shore system, for example, you could use a PSM 900 transmitter, and you can use what is it? Help me out. Their U series receiver. So you can end up with both pieces that have, you know, AC to them. You don't have to use batteries or bell packs, and then you could use an antenna like that. So if you had to hit a speaker 200 or 300, maybe 400 feet away, you could do that with two CP beams, one on the transmitter and one on the receiver.
Awesome. Thanks.
Did that answer that question? I'm not entirely sure.
Always, Don, always. This is a good one. It comes up a lot over here. What would be the best practice for using more than 8 IEM transmitters? Keep combining or use multiple antennas?
You're right. Okay, so working with wireless, it's always about trade-offs, as is working with almost anything. We recommend that you don't send more than 8 signals to a single antenna. Other manufacturers will tell you you can do 16. We're both right and we're both wrong. The more you use, the more intermod you're going to create. And so as long as you can keep that 20 dB, but it starts growing very quickly, right? So, you know, 9 isn't just a little bit more than 8, it's a lot more than 8, and 10 is a lot more than that. So it's a reliability trade-off. I have people that do it. You know, if you're on a mountaintop in Idaho, you're probably going to get away with it. If you're in downtown Manhattan, you're probably not gonna. I would tell you that the biggest concerts, you know, you go see, you know, somebody at the Megadome, they usually cut it off at 4. They need the last, you know, tenths of a percent because, you know, they got to get it right. You know, and so they typically will only combine 4 to an antenna. And so it's a trade-off for reliability. But we think 8 is a good number. You know, you can take your chances, and it may work perfect for you, or it may be perfectly horrible. That requires some measuring. We'd have to go out and do a site survey. I could give you a better answer, but we think 8 is a good place to cut it off. So if you've got more than 8, then you want to use a second combiner and another antenna.
Excellent. So down to the last few here. So see, hopefully this one will be quickly here. So is there a best practice on the right frequencies to use?
Well, the simple answer, of course, is yeah, anything that's unused. I mean, so we all have, so in the United States, and I know some of you guys are other places that are watching us today. Thank you for joining us. You know, in the USA, we have 470 to 608 essentially, with a very few exceptions. What I will say is that with all radios, your wireless mics and your ears, the lower frequencies will transmit farther than the higher frequencies with the same amount of power, right? Kind of like the same way with your speaker system. It takes a whole lot more watts to generate power for your subwoofer than it does for your super tweeter, right? 1 watt at the top is equal to thousands at this end of the sub. It's not quite that big a spread, but lower frequencies will go farther than higher frequencies. But the frequency you transmit by itself, with the exception of that power, it doesn't affect the quality, right? So transmitting in VHF, UHF, 2.4 gig, 5 gig, those don't directly affect the quality of the radio. As long as everything else is right, the radio doesn't really care what frequency it's broadcasting. But lower frequencies transmit farther than higher frequencies given the same amount of power. But there's not really, I don't have no problem using mics or ears at the low or the high end of the band. It's not a big deal in the US between 470 and 608. It doesn't make very much difference at all. It's more on paper, but not in the real world.
Excellent. So I think we have time for probably one more here. So
okay.
see here. In a setup where the control is in the center and receiving IEM signal is required directly to the left and right, about 300 feet each way with clear line of sight, what would be the setup or antenna that's required?
What you have to do in that kind of a situation, well, there's two ways to go. I mean, you could use a single, you could use a single whip, right? Which is going to be essentially omnidirectional in the horizontal, but you'll never get that kind of distance out of it. So in a practical sense, what you're going to need to do is use two CP beams, two circular polarized, otherwise called helical antennas. And you're going to have to, you'll take the output of your combiner and run it into a 2x1 splitter, and then run the two outs to each of those in each direction. But I got to tell you, that's an awfully long distance, 300 feet on both sides of those, because when you run the splitter, you're essentially taking your power and running half of it to each antenna. So you've knocked another 3 dB off your signal. So that would be difficult. But if you had, I guess if you were set up in the middle of two football fields that were end to end, that's the way you do it. I see this happen a lot of times in television broadcast studios where they've got spots all over the place and they have to do that. And frankly, to do that is a much more expensive thing. We do get into high power booster amps, which are expensive, right? You're talking about things that are $800 or $1,000 a piece, and you might need a bunch of them. So that's a very specialized, that's a specialized use that, I think mainly we're talking here today about people, bands, musicians, right? People that are on a stage. So to do it otherwise is going to be kind of a specialized thing, and it's doable, but it does require some special, read that, expensive parts.
Okay, awesome. Well, I think we've come to the end of our time here, and to those who asked questions that we weren't able to address, we will try to follow up with you on email to answer your questions. But as always, you can email Don directly with his email address on the screen, or you can email me, adam@rfnu.com, and we'll be happy to clarify any questions you may have about the webinar, about RFNU products and IEM systems in general. So we thank you very much for attending this webinar. We hope you found it productive. As well, we'll be sending you a follow-up email with a short 2-minute survey just to see how we did. We love hearing your feedback as always. So thanks again. We appreciate your time, and I hope you enjoy the rest of your day and week and have a wonderful holiday.
Thanks, guys.